Everyone. Today in this video, we would like to talk about a concept called simple pendulum. So we will describe, explain what's the meaning of simple pendulum and then go into the details further, right? So what's a simple pendulum? A system, a setup, is in simple harmonic motion. How do you say someone is in simple harmonic motion? It has to be oscillatory motion. Its acceleration is directly proportional to displacement, and acceleration and displacement shall be in opposite direction. So these three conditions has to be satisfied. Oscillatory motion, acceleration directly proportional to displacement, and they are in opposite direction. So taking that basic definition of a simple harmonic motion into consideration, let us define what do you mean by a simple pendulum itself. Pendulum, it oscillates, right? So what does a simple pendulum has? It has a fixed support, fixed rigid support. So there is some support, fixed support, rigid support, right? To that fixed support, we'll have a wire, thread. What's the properties of this thread? It is lightweight. We don't count the mass of this thread into consideration. So it shall be a lightweight and it is inextensible. It shall not expand itself. So we shall have a inextensible string. And at the bottom of that light-weighted inextensible string, we shall have a mass. It's a heavy mass. It is point-sized mass. We can call it like a simple pendulum. So, what is a simple pendulum is? If you need to look at the definition, a heavy point-sized mass suspended to a fixed rigid support with the help of a light-weighted inextensible string is called as a simple pendulum, right? So when you apply a little kind of a force horizontally like this, it will deviate its position from this, which is a rest position called as a main position, and makes an angle theta with the vertical, right? So it's oscillating about the main position. It go from main position to this side, extreme, and it will come back to the main position and go to the other side, that is interim position also. So this is having a oscillatory motion, and we'll be proving that acceleration is directly proportional to displacement and in the opposite direction. We can also prove it in other way. Not this is a linear acceleration. Other way of saying its angular acceleration is directly proportional to angular displacement. Both are same, depending on how do you try to prove it. We will try to prove it in this way, a little more technically sound way, right? So now we know being what is a simple pendulum is. It's a lightweighted, heavy, lightweighted, inextensible string to which a point and heavy-sized mass suspended from a fixed rigid support. Then I want to tell you one more small point. What is the length of a simple pendulum is from the center of that bob, heavy point-sized mass, to the point of suspension. Be careful, not to the bottom, to the center of point-sized mass to the point of suspension. The distance between them is called length of pendulum, right? Let me call that length of the pendulum as L, whatever. So as we understand the definition of a simple pendulum, let us try to derive an expression for the time period of a simple pendulum. Yeah, let's do that. Yes. So I will redraw the diagram once again for you. A fixed rigid support with the help of a light-weighted inextensible string, a point heavy sized mass is suspended. When it is slightly disturbed by applying a force, it is simply pulled to a side and its vertical displacement with the vertical and angle theta. So it happened this way. Here it is having some mass. So its weight always acts in vertical direction, which can be resolved into components. As this angle is theta, this is also theta. This becomes adjacent to theta, so it becomes mg cos theta. It is opposite to theta, so it becomes mg sin theta. In this string of length L, there is a tightness generated that is called something like tension. So what we can see is, if you imagine a kind of a oscillatory movement, a circular motion. Oscillatory motion is a part of a circular motion. So this bob starting from here is in a circular motion like this, a big circular motion. Among this, we are considering a part that is a oscillatory motion, right? So taking that into consideration, that oscillatory motion into consideration, the force acting towards the center of the circular motion, force towards center of that rotatory motion is towards the center, there is a tension T. Away from the center, there is a force mg cos theta. That is the total force acting towards the center. The question is, will this be able to produce any turning effect in this oscillatory motion? So to produce a turning effect, we shall have a torque. We know the definition of a torque is force into perpendicular distance. And then torque can be written like F x sin theta. Now, force we know already. And the distance of that rotatory motion is from this point to this point, that is length of the pendulum. Sine angle is 0 because this force and this L both are in the same direction. Sine 0 is 0, so the torque is 0. So no turning effect towards the centripetal direction, towards radial acceleration or centripetal acceleration. Though the acceleration is there, there is no turning. Let's talk about the other part. This part, mg sin theta is in this direction, L is in a different direction, so there's a turning effect due to that. So what we can say now, let's find out the turning effect of the other part. So the torque due to um, mg sin theta, this part is acceleration of force into perpendicular distance. The perpendicular distance is L, so that is the force and perpendicular distance. If the angle is small, that's a condition for this body, for the system to be in simple harmonic motion. Sin theta is close to theta. So be careful. Simple pendulum is in simple harmonic motion only when angular displacement theta is small. We shall not pull to a very large. In that case, I can rewrite the above equation, torque as mg L theta itself. I can put a negative sign here because this torque, this mg sin theta is the force that is trying to pull the body towards the oscillatory position. That's why that kind of a force is called as restoring force. The force that is trying to get back to its original position. So to say it's a restoring force, I have written a minus. I know tau can be written like I alpha, where I is moment of inertia. Moment of inertia of this system is mr square. R is nothing but L square, where m is the mass of that body, L is the length of that pendulum. So ml square can be written like minus mg L into theta. M can be cancelled, 1L can be cancelled. So of course, I alpha, there is an alpha. So L alpha equal to minus G theta. So alpha can be written like minus g by L into theta. Alpha is called angular acceleration, theta is angular displacement, g is a constant, length of a pendulum, inextensible string, therefore L is also constant. So this is uh, similar to what we have written like earlier, this equation. Acceleration is equal to minus omega square y. Here A is linear acceleration. If you write it in terms of angular acceleration, alpha equal to minus omega square. Instead of linear displacement, angular displacement theta. So both of them are perfectly coinciding with checking with each other, right? In the place of acceleration, we have angular acceleration. In the place of displacement, we have angular displacement. Minus and minus are there. So omega square, what is there in the place of omega square is g by L. From this implies we can say alpha equal to minus omega square into theta. So what is there in the place of omega square is g. L is the length of the pendulum. So omega equal to square root of g by L. Omega can be written like d theta by dt. When one rotation is completed, angle covered is 2 pi. Dt is the time taken for one rotation that happens as with one oscillation, that is t. So in the place of omega, I can write 2 pi by t equal to root of g by L. So time period of simple pendulum is 2 pi into root of L by g, where L is the length of the pendulum and g is the acceleration due to gravity. This is the way that we can find out the time period of simple pendulum. Well, I want you to see this video once again right from the beginning to get a say the things are fixed into the head so that we'll have a clarity. For any kind of a clarification, you can just comment under this video. Thank you for watching.